Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll begin the second part of refraction of light and talk about a few advanced concepts. The first concept I want to discuss is when two thin lenses are separated by a distance. So we've done what happens for one single thin lens, but what happens when two thin lenses are put together. Now it actually ends up becoming quite mathematically complicated, so we'll take a special case, that is, we'll take parallel incidence. That means initially the object is kept at infinity and parallel rays are coming. Right. So first it will be deviated a little bit and go like this, then it will be deviated a little bit more and maybe go here. Let's say this is A, let's say this height is h1, this height is h2, let's say this angle is delta 1, the deviation produced by this lens, and let's say this angle is delta 2, the deviation produced by the second lens. The total deviation will be delta 1 plus delta 2. Right. Also we know that delta 1 will equal to h1 by f1, because if there were no lens, that would meet at a point f, and then h by f would be the angle. Similarly, delta 2 is equal to h2 by f2, and what we want is a single lens that would be kept at a particular position, which would ultimately give the exact same image as the combination of these two lenses. So for that lens, the total deviation, let's say it will be h1 by f, which will be the focal length of that lens, right? And we know delta is equal to delta 1 plus delta 2. We need to find out this focal length f of the new lens and where it should be placed. From this we can easily get h1 by f is equal to h1 by f1 plus h2 by f2. Another result we can see is that h1 minus h2, which is this distance, delta 1 by h1 minus h2, sorry, not delta 1, my mistake, but d, this distance is d, d by h1 minus h2 is equal to cot of delta 1 from this triangle, right? From that we can get h1 minus h2 is equal to d tan delta 1, and tan delta 1 I can write it as h1 by f1 because delta 1 is very small. So h1 minus h2 is equal to d h1 by f1, which gives me the final result here, one of the final results, h2 is equal to h1 times 1 minus d by f1. And this is already decided. Once you put this lens here, the amount it will deviate is already decided without this lens. So this h2 is independent of this length actually, right? From this we can see if we put this here, sorry, this should be plus, and if we put the value of h2 here and divide it by h1 all sides, we'll get 1 by f is equal to 1 by f1 plus 1 by f2 minus d by f1 f2. So this is the equivalent focal length, and you can see if d was 0, we got 1 by f is 1 by f1 plus 1 by f2, which we know already to be true. Right. If there were just two lenses kept side by side, then the net power is equal to the sum of the power of individual lenses, power being 1 by f. So if there's a thickness d between them and its parallel incidence, then the equivalent focal length of this combination would be such that 1 by f is 1 by f1 plus 1 by f2 minus d by f1 f2. Also, let's say that that lens was placed at this point and we want to find out this distance. Right. So in that case, what we can do is, if we assume that there was just one lens here, then this ray would have gone parallel like this and have been deviated by an amount delta to give the same deviation, right? So we can see that pp2, this is equal to this by delta, right? So pp, if this is p and this is p2 and this is p1, pp2 is equal to h1 minus h2 by delta, because h1 minus h2 by pp2 would be delta, right? Tan delta or rather delta. So these are the two formulas that need to be remembered. One is that the equivalent focal length will be 1 by f1 plus 1 by f2 minus d by f1 plus f2. And where should it be kept? It should be kept at a distance of h1 minus h2 by delta from the second lens, from the lens that is behind. Another concept that is of relative importance is another type of magnification. We've seen what what magnification is, height of image by height of object. That is generally called the lateral magnification. There's another type of magnification called the longitudinal magnification. This is also called transverse magnification, by the way. We've seen the terms transverse and longitudinal before as it relates to waves, and it's pretty similar here as well. So if this is a lens, longitudinal magnification tells us if this is an object of height h, then what would be the ratio of the height of the image to the height of the object. That is transverse magnification. Longitudinal magnification tells us if we keep an object of length L like this, what will be the length of the image. The length of the image by the length of the object is called longitudinal magnification. I'll just write it as LM right now. This we'll refer to it as TM, transverse magnification. Right? And how do you calculate that? That's actually quite easy. Essentially what you need to do is, this object, this point will have an image here, and this point will have an image here. Find the distance between these two objects, find the distance between these two images, and the ratio of them will be the longitudinal magnification. However, there is an easier way to do this. Let's assume we have a point here and that forms an image here. If we move the point a little bit towards the right or towards the left, the image will move a little bit as well. And the ratio of the movement of the image to the movement of the object can also be taken as longitudinal magnification. Right? And what is that equal to? That is equal to dV by du. The derivative of v with respect to u, or a small change in v with respect to a small change in u. Remember, transverse magnification is v by u or minus v by u or something like that. Longitudinal magnification, dv by du, and you can always differentiate v with respect to u using 1 by v minus 1 by u is equal to 1 by f. Now there is one small concept which I forgot to mention in the first refraction video, and that is the concept of total internal reflection and the critical angle. It happens when you have rays going from a heavy material, let's call it mu, to a lighter material, let's call it 1. Now if you have a ray of light going like this, then it will bend away from the normal and it will go like this. Right? If you have a ray of light going like this, then it will bend even more and go like this maybe. If you have a ray of light that's extremely large angle of incidence, then it might actually go parallel to the surface, because that's how much the refraction would be, or the deviation. And if this angle of incidence is slightly more than this particular angle for which a ray is parallel, then the ray actually comes back. And this phenomena of a ray coming back is called total internal reflection. And how does this occur? So we need to find out the angle of incidence for which the angle of reflection will be 90 degree. And that's easy enough. Mu sine I is equal to 1 into sine r. Sine r is 90 degree. So 1. That means I is equal to sine inverse of 1 by mu. Right? And this always happens from a denser to a rarer medium, by the way. From a rarer to a denser medium, you never have total internal reflection. So if light is going from a denser to a rarer medium and the angle of incidence is greater than this critical angle, this is called the critical angle. And if the angle of incidence is greater than the critical angle, then the ray will be completely reflected back, and that phenomena is called total internal reflection. This completes the refraction of light. In the next set of videos, we'll start discussing various optical instruments such as a telescope or a microscope. Thank you.